We are going to start with a list of all the stuff that you should know. I'm not reteaching this to you. I'm expecting that you already know this. First one, I'm expecting that you know how to tell me the dimensions of a matrix. If you don't, go back and look at it. I'm expecting that you're able to tell me when two matrices are equal. That one is intuitive. When do you think two matrices are equal? All of the components are the same. Okay, following operations you should remember. You should remember how to add matrices, subtract matrices, how to multiply a matrix by a constant multiple, and lastly, how to multiply two matrices. If you don't, go look it up. Sound good? Okay. One thing I believe you've learned, I think, but probably don't remember, is the transpose of a matrix. So a matrix like this. Do you know what transpose means? Kind of. You switch the rows and columns. We're going to do an example. So each row becomes a column instead. So if we consider the following matrix A, just for fun, what are the dimensions of this matrix? 3 by 2, always rows by columns. Okay, transpose of a matrix. Every row becomes a column, or every column becomes a row. So in this case, first column is going to become the row 1, 3, 4. Second column will become the row -1, 2, 0. So this matrix then is 2 by 3. Have you guys seen transpose before? Okay, beautiful. Could I add these two matrices? No. Could I multiply them? Yes. Do you remember that the inside numbers have to match? What will be the dimensions of the answer matrix? 3 by 3. Now, if I multiply these two, I'm not going to get anything special. I'm not going to get the identity or something. I'm just going to get a new matrix. Next thing we need to talk about is the multiplicative inverse. Let A be an n by n matrix, so a square matrix. If there exists an n by n matrix B such that A times B or B times A gives us the identity, then we say that B is the multiplicative inverse of A. I think in the past you guys probably just called it the inverse. It's a multiplicative inverse though. Okay, here's the notation. So B is the inverse of A. What is the identity matrix again? Ones on the diagonal, zeros everywhere else. Does that sound familiar? Okay, so one thing that's important to know is only square matrices have inverses. So if you have a 2 by 3 matrix, it's not going to have an inverse. It has to be a square matrix. Do you know if I have a square matrix, so I have a 2 by 2 or a 3 by 3 matrix, do you remember how to tell if that matrix does in fact have an inverse? Because not every matrix has an inverse. Don't remember? Okay. We're gonna write down a definition that is gonna answer that question. If A is n by n and the determinant of A is not equal to 0, A is called non-singular. if the determinant of A is 0, then A is singular. Now, when do you think that A will have a multiplicative inverse? Correct. So an n by n matrix A has an inverse. What does IFF mean? If and only if A is non-singular. Okay. Do you all remember how to find determinants? Up to 3 by 3? Well, we're only going to do up to 3 by 3. You should be okay after 3 by 3. 4 by 4 is exactly the same as 3 by 3. Yeah, it is. It's a whole lot more work.
Oh, do you make 3 by 3? Do you do
You're gonna make
one
4.
The determinant of the 3 by 3, and then do those.
Yep.
Make 4 3 by 3s, and then you do 4 3 by 3s.
Yep.
That's horrible.
Okay, so the next logical task is finding the multiplicative inverse. This is going to be slightly tedious, just so we know. Not difficult, but tedious. Okay, let A be n by n and non-singular. So in other words, let A have a multiplicative inverse. Okay, let C of ij be negative 1 to the I plus j m of ij, where m of ij is the determinant of the n minus 1 by n minus 1 matrix that is obtained by deleting the ith row and jth column from A. The inverse then is going to be 1 over the determinant of A multiplied by Cij, the transpose. Okay, I understand that this makes pretty much no sense. So basically what we're going to do is we're going to find the inverse, and I'm going to show you what this means. Okay, are we okay if we just jump into an example that uses numbers?
Yeah.
I was going to do one with variables, but I think numbers will be easier. Okay, we are going to find the inverse for matrix A, which is the square matrix 2, 5, 1, 4. Okay, before we even start messing with the C's, we're going to need the determinant of A. So let's start by that. How do you find the determinant of a 2 by 2 matrix? Okay, I saw a bunch of this. So 2 times 4 is going to give us 8. Subtract 5 times 1, which is 5. This gives us 3. So that's our determinant. Notice the determinant is not 0. Because our matrix is 2 by 2, it's square, and because our determinant is not 0, that's how we know that the inverse does exist. Okay, so our inverse is going to be 1 over the determinant of A times all of these C's. We're going to start by finding all of the C's. Here's what this means. So it's still going to be 2 by 2. When I am looking for this component, I ignore that row, that column, and find the determinant of what's left. Now, in this case, all that's left is a single number, So that's what would go there. It's 4. If I'm looking for this component, I ignore that row, that column. What's left is a 1.
Is this to just find the C's?
Yes. When I want to find this component, I ignore that column and that row. I'm left with a 5. When I want to find this component, ignore that column, that row. I'm left with a 2. So those are the C's. Next thing we need to do is we need to take care of that -1 to the I plus j. This component, first row, first column. So I and j are 1 and 1. -1 squared will give us positive. This one, first row, second column. So 1 plus 2 is going to give us 3. -1 to the third means this is going to be negative. Down here, second row, first column, again 3, this will be negative. Second row, second column, 2 and 2 is going to give us positive. Okay, this now is the C of ij. Bless you. Next thing we're going to have to do is take the transpose.
How did you find the signs? Like positive and negative?
Yeah.
Yes. So the sign here is positive. First row, first column. I and j are 1 and 1 then. So I and j denote the row number and the column number.
So are rows I's or are they J's?
In this notation, I is the row, j is the column. Doesn't matter though, because you're adding them. Okay, with me now? Okay, transpose. So this row becomes a column. So this is 4, -1. This row becomes a column. So -5 and 2. So finally our inverse is 1 over the determinant of A. So 1/3 times 4, -5, -1, 2. Now, you could multiply the 1/3 into everything. I think that makes it look a little bit messy. So oftentimes we just leave the constant out in front. Okay. If I asked you to verify that A and this matrix were in fact inverses, what would you do? Multiply them. And what should you get?
1, 0, 0.
Right, the identity matrix. If I multiply this way and I get the identity, am I done? No. You have to multiply the other way as well. That was part of the definition of being a multiplicative inverse. Right here, A times B and B times A have to give you the identity. You can't just multiply one way, you gotta multiply both. How do you like inverses? Don't worry, we're gonna do another one. I want to find the determinant of A. Ideas? Come on, guys, you told me you knew how to take the determinant of a matrix.
3 times -1 minus 2, right?
Yeah, I could do that.
Oh.
I'm trying to do the least amount of work.
Use the right.
So you can choose any row, any column. I'm going to choose this column because I have a 0 then, so I have less work to do. So this will be 1, and then ignore row and column, times the determinant of the remaining matrix, minus 0 times the determinant, I don't care though, that's going to give me 0, plus -1 Again, ignore that column, that row. I get 3, 2, 4, 1. I'm assuming that you can do the computations. You get 27. Okay. So then we're going to get our C matrix next. It's going to be a 3 by 3. I'm going to help you find the first 2 terms, and then you're going to find a few. If I want C of 1, 1, so I want the first component, I'm going to ignore that row, that column, and do the determinant of what's left. So -1 minus 0 would give me -1. If I wanted C of 1, 2, so first row, second column, that one, ignore that row, that column, determinant of what's left. So in this case, -4. I would like you to take a minute to find the remaining components and figure out the signs. So do the -1 to the I plus j. Good luck. Okay, so for this one,
Yeah.
so for this component, ignore that row, that column, take the matrix that's left.
And then, take the determinant of that matrix.
Yep. When you get a few terms, check with the person next to you just so you're not going the whole direction the wrong way. Wherever you are, check with the person next to you, please.
I think that's what it says.
This is what I got as my final answer. So there's a whole lot of steps. These are, without the red, are the initial C's you should have gotten. Next thing I did is I did -1 to the I plus j. So you end up with alternating signs. That's not always the case. So last example we did, it wasn't alternating from one row to the next. Then you have to remember to do the transpose also. How'd that go besides being tedious? Alice?
I just have like a verification question. So
Mhm.
the sign that you get, you're basically multiplying to the number. Bless you. Like if I like for like the -4 in the.
Yes. So it's a
yeah,
negative
multiply, so
-4.
that becomes positive.
Yeah.
Okay.
Yeah.
Did you say that the opposite signs, it's not always like that?
It's going to be in the row, but it's not necessarily going to be positive to negative to the next row.
But how so?
Oh.
Because the rows and columns will always
It's
be
gonna be the
constant.
same pattern, but
It's the same pattern, but never
you
the
just
same.
can't go like plus
Because
minus
if
plus
it's 4
minus.
by
Like
4.
with the actual numbers, but the signs added on to the numbers should always be the same, right? Like it'll always look like that for the extra signs from the -1.
Yeah.
Yeah.
So yeah, so what I'm telling you is it's always going to alternate this way, but it's not necessarily going to alternate from the end of one row to the beginning of the next. Like if we went to the previous example, alternated, but it was same again. So that's what I'm saying is don't just do the first one and then go plus minus through the whole matrix.
Okay, but for 2 by 2, that's always going to be the structure.
Yeah.
Yeah. But like, I don't know. I don't think. Okay. I was in.
Do you get what the point
Yeah,
I'm
I get
trying to
what
get
you're
across?
saying, but like the alternating, I see is more like around and then up through the rows, not necessarily like snake.
Okay,
through
how-
the rows.
However you
Okay.
want to do it. Okay. We good on determinants or inverses because this is not even what I wanted to get to today yet.
Okay.
Okay, so I can go on? Okay. Next thing you need to know. We're not going to do any examples. Calculus of matrices is what you think it would be. In other words, if I gave you a matrix and I asked you to find the derivative of that matrix, what would you do?
Take the derivative of each number.
Take the derivative of each component. Yeah. If I asked you to find the integral of a matrix, what would you do? Integrate of each component. Sound good?
So like if you have a number matrix, all of them will be 0 once you take the derivative.
Yeah.
Oh,
So I wouldn't ask you to do that. I would give you variables
It's on
in your
the test that
matrix.
I need to study for.
I already told you this is not on your test. Okay, this is what I finally wanted to get to today. Solving systems using matrices. Do you guys remember doing this previously
No.
RREF?
with RREF?
Yeah.
Okay,
On the calculator.
we are not going to be using a calculator. You will be doing RREF by hand. So, that's where the rest of this is going. One thing you need to know is an augmented matrix, which you guys have seen this before. Augmented matrix, when you were solving systems, looks like this. All of the A's were your coefficients on X, Y, and Z. The B's were kind of the answer in your system. Looks something like this, more condensed. Okay, here's what you're going to need to do when you have this augmented matrix. You're going to need to perform elementary row operations. There are 3 main elementary row operations. First one, you can multiply a row, a single row, by a non-zero constant. So all of this is trying to solve a system. You're going to use these row operations. You can interchange rows. And lastly, you can add non-zero constant multiples of one row to another. We are going to use elementary row operations until we have an augmented matrix in row echelon form. This is not the same as reduced row echelon form. Row echelon form. To get there, we're going to use Gaussian elimination. Okay, Gaussian elimination is going to get us to row echelon form. Row echelon form has three different properties. The first property is that the first non-zero entry in a non-zero row is 1. Second property is that in consecutive non-zero rows, the first entry 1 in the lower row appears to the right of the first one in a higher row. And lastly, all 0 rows are at the bottom of the matrix. Okay, I know that's a lot of words, so I'm going to show you what I mean. You're going to have an augmented matrix. You're going to have some numbers here. The diagonal has to have 1s or 0. Everything below that is going to be a 0. Up here are any free numbers. So every first entry in the row has to be 1, unless it's a 0. 1's on the diagonal, 0's at the bottom. So this is called row echelon form. We would have used Gaussian elimination to get here. And we're going to do an example to show you how to get here. If we were doing Gauss-Jordan elimination, you're going to keep going until each column has a 1 and there are 0s elsewhere. So that would be something like this. This you've seen before. This is the reduced row echelon form. To get here, you would have used Gauss-Jordan. So basically, to get here, you do Gaussian elimination, and then you have a few extra steps. Okay. Is this example 4, I think. So we're going to solve this system first by just plain old Gaussian elimination, and then we're going to do Gauss-Jordan. Starting with Gaussian. This has a lot of steps, so it's very important that you follow me and that the first time I lose you, you let me know. First thing you need to do is you need to form your augmented matrix. So you're going to take all the coefficients, 2, 6, 1, and then you're augmenting that with 7, 1, 2, -1, -1, 5, 7, -4, 9. Ultimately, what we need is we need 1s on the diagonal, we need 0s here. First thing that I notice is that this row starts with a 1. So it would be very convenient if that were my first row instead of my second row. So what I'm going to do first is I'm going to switch rows 1 and 2. Now, when people do this, they'll write their steps here. So you would write something like R1, 2. What that means is I'm switching rows 1 and 2. There's no particular reason I chose 1 and 2. I could have chosen, no, would have had to use 1 and 2 because I want 2 there. Okay. What else I need? This one is good. Next thing I need is I need this number to be a 0, and I need this number to be a 0. Right? Because we need 0s below our 1s. Elementary row operations, I'm allowed to add rows, and I'm allowed to multiply by constants. So what I could do is I could take the first row, and I could multiply it by -2, and add it to the second row. If I do that, this will now be a 0. With me? Multiply this row by -2, add it to this row, that'll be a 0. Likewise, I could take the first row and multiply it by -5 and add it to the third row. If I do that, this would become a 0. So first row we don't touch because it has that 1 that we want. Multiplying this row by -2. So this will be -2 add 2, which is 0. This will be -4 add 6, which will give me 2. This will be 2 add 1 will give me 3. This will be 2 add 7, which will give me 9.
Shouldn't the one above the 9 be -1?
Yes. Thank you. Multiplying this by -5. -5 add 5 gives me 0. -10 add 7 will give me -3. 5 add -4 will give me 1. 5 add 9 will give me 14. Okay. It was a good thing Helen pointed this out. If we had dropped that negative, we would be in trouble for the whole rest of the problem. So every step matters. So you have to be very careful. Next thing we need this number to be a 1. So I'm going to divide that entire row by 2. So the next thing that I'm going to do is I'm going to take row 2 and I'm going to multiply it by 1/2. So again, row 1 is exactly the way we want it to be. I'm taking half of row 2, so this will give me 0, 1, 3 over 2, 9 over 2. And row 3, I'm going to keep the way it is. Okay. We needed 1s on the diagonals. That's good. Joe, do you have a question?
No, sorry.
No, it's okay. We need 0s below, so that needs to be a 0. How am I going to get that to be a 0? I'm going to multiply row 2 by 3, and I'm going to add it to row 3. Could I use row 1? Yeah, then I would end up with a number here again, so counterproductive. So we have to use row 2. So then second row stays the same. Okay, I'm multiplying this row by 3 and adding it to the third row. So I get 3 add negative 3 is going to be 0. I get 9 over 2 add 1, which is going to be 11 over 2. And then 27 over 2 add 14, if you trust me, is 55 over 2. We're almost there. Now, what messed us up is we need a 1 there. So what am I going to do? Multiply by 2 over 11. So I'm going to get 2 over 11 times row 3. Okay, so here's how we know that we are in row echelon form. Row echelon form. 1's on the diagonals, 0 below the diagonal. Now you are able to solve this matrix. Bottom row tells us that z equals 5. Middle row tells us that y add 3 over 2 times z is going to be 9 over 2. Top row tells us x add 2y minus z equals negative 1. Can I trust that you're okay solving this? If you trust me, the answer is 10, negative 3, 5. Okay. Now, that was Gaussian elimination. Nathan?
Were we supposed to have the all 0 row at the bottom? Or not?
No. So sometimes there will be, sometimes there's not going to be. But if there is, 0s has to be at the bottom. Okay. We have 2 or 3 more steps in Gauss-Jordan to get to reduced row echelon form. So again, copy that matrix we have. Okay, with reduced row echelon form, on the left side, we need the identity. So we have 3 terms right now that are an issue. That needs to be a 0, that needs to be a 0, and that needs to be a 0. Let's focus on the second row first. How can I get rid of that 3 over 2?
Multiply row 1 by 2 over 2. Or no, that would make.
You can multiply the bottom by negative 2.
Row 3 by negative 2.
Don't I want to multiply the bottom row by negative 3 over 2? Right? Okay. Whew. So negative 3 over 2 times row 3, I'm going to add that to row 2. Oh man, you guys are... Sometimes you guys make me think that I'm the one that doesn't know what I'm doing. Because you all are so convincing. Okay, so 0 add 0, still going to be a 0. 0 add 1, still going to be a 1. Negative 3 over 2, add positive 3 over 2 is going to be 0. Negative 15 over 2, add 9 over 2 It's going to be negative 6 over 2, which will be negative 3. While I'm at it, what else can I do that's going to be helpful in getting rid of one of those two?
Multiply the new row 2 by negative 2.
What? Yeah, I could do that. I'm going to have to eventually. I'm going to add row 1 and row 3 together to get rid of that negative 1. So 0 add 1 will give us 1. 0 add 2 will give us 2. 1 and negative 1 gives us 0. 5 and negative 1 gives us 4. Last remaining holdout is that 2. So 2 is the issue. Okay, I don't need to do anything with row 2 or row 3 because those are in the form that I want already. How am I going to get rid of that 2? Multiply negative 2 by the second row and add it to row 1. So 0 add 1 will be 1. Negative 2 add 2 will be 0. 0 add 0 will be 0. 6 add 4 will give us 10. And there is the answer that we found before. Don't you feel so accomplished now, knowing where reduced row echelon form comes from?
I think we knew this before. Like freshman year. We did this.
No, there's no way you did this freshman year.
I remember doing this.
I remember just